Now, having done this, how do you actually write these limits? That's very, very important and interesting. Because my integration was with respect to y, I traveled vertically from the innermost boundary layer to the outermost limits of x, which is the first order of integration. You can see that I incept my journey from y axis and travel horizontally to meet this straight line. So y axis is this is the straight line. So these two examples must completely give you the holistic picture. Now let's try and look at one more important component of curriculum, where a given double integral would have a certain order of integration. That is maybe first with respect to x, then with respect to y, or the other way around. And what you are supposed to do is change that order of integration, and therefore it is quite obvious that you are also going to change the limits of those integrals. Previously we have seen how a double integral is employed to produce area, volume, all that. Subsequently we also introduced you to the idea of limits, how they are reckoned from the geometry over which the integration is carried out. Now let's try and look at typical exam oriented situations wherein we are going to change the order of integration and then graphically reckon the new limit when you change the order of integration, and then evaluate them to get a numerical answer. Now the first question is as follows. This is the given integral whose order is the outermost integration is with respect to x and the innermost is with respect to y, because of course there are only two orders, and we need to change this order. First we need to integrate with respect to x and then subsequently with respect to y. That is the question, and of course you will have to evaluate once you change the order of integration. But that apart, let us make some very, very important observations. Observation 1, you can see that the limits that I have put for the outer integral, that is 0 to 1, are fixed numbers, whereas the limits for the inner integral, that is when you are integrating with respect to y, have got variable limits. This very, very clearly means that your boundary definitions are actually not straight lines, either parallel to y-axis or parallel to x-axis. Because the moment you say the limits are variable, either your boundary definitions are inclined straight lines or curves. That is observation 1. So therefore, observation 1 is very, very clear that if you have variable limits for the inner integral, of course, that is the first integral, then this actually means that boundary definitions are either inclined straight line or a curve. Inclined straight line, or it can be a curve, right? So this is very, very important for you to observe. And then once this is understood, the second thing that you got to do is figure out the area over which you are integrating. Once again, let me tell you that we are integrating xy over certain region which are going to be defined by these boundary definitions. And if xy were to be 1, then you would have exactly got the area over which the integration is supposed to be carried out. So now you are integrating a function f of x comma y over a region which is defined by these boundary definitions. Now, how do you actually come out with the area that we have represented, which is in parrot green, over which you carry out the integration? Numerically, what happens first, let's understand before I construct this figure. At every point, let me make an infinite number of dots, because when you say integration, it is infinite number of points that you would be accounting for For all these dots within this area, you compute x coordinate, y coordinate, that is abscissa ordinate, take the product and then add it up. So that is what this integral represents numerically. For every infinite number of dots that go to constitute this particular area, the dots are proliferated across this area. Those which constitute this area have got x and y coordinates which are multiplied, that is xy, and then added up. That gives you the value of the integral. So, but how do you actually construct this particular area? It's very simple. Go by the definition. So the first, the lower limit is given by y is equal to x square. So what is this? Your basic coordinate geometry, either 10th grade or +2, tells you that this is a parabola that is symmetric about y-axis. Why do I say that? Because whether you put in x plus x or minus x, y is going to remain positive, because your y is a square of x. That means it's an even function. It's an even function. So whether this function has a minus x as input or plus x as input, it always gives you a positive value of y. The power is 2, so it's an even function. And what about the next limit? That is y is equal to 2 minus x. So this clearly means that it is a straight line with negative slope and positive intercept too. Two ways of representing it. One of the simplest ways of representing a straight line, what I would prefer for your curriculum, is y plus x is equal to 2. Divide both the sides by 2, you get the intercept form of the straight line, which means that your x-intercept is 2, y-intercept is also 2. And that also goes with the negative slope, because you can see that if I draw the straight line like this, this has got negative slope, because you can see it makes an obtuse angle with positive x-axis. And this is y is equal to x square, the parabola. And what about this? This is nothing but x plus y is equal to 2, and that's what exactly we have sketched here. This region is constructed using the limits of the inner integral. For all the problems to follow, the same methodology is going to be adopted. That's very important. And obviously this point has to be determined, because this is the point where the straight line and the parabola meet each other, and that is going to stipulate the boundary. Beyond that, you are not evaluating your integral. Your integral evaluation stops at this extreme point. And what is that extreme point? That extreme point can be got by simultaneously solving y equal to x square and x plus y is equal to 2. That's quite easy to do, because what I can do is I can substitute here, instead of y, 2 minus x, which is equal to x square. And this is a quadratic equation. It will give you two values. One is negative and one is positive. Why do you get two values? Because if I extend this line, it's going to cut the parabola somewhere in this particular quadrant where y is positive but x is negative. But the positive value of x is sought because it's going to intersect in the first quadrant. And you can solve this quadratic equation, but you can verify whether if I put x equal to 1, whether I will get y is also equal to 1. Obvious, because x equal to 1 will give you, if you put in any of the equations x is equal to 1, y you will get as 1. Here also, if you put x equal to 1, you get y is equal to 1. So this point is 1 comma 1, and you can see that this point is 1 comma 1. So this is the extreme point, and therefore if you looked at the limits of the x, the limits actually incept from 0 and it goes up to 1. So that means 0 to 1, this is the extreme limit. Clear? So what did we do? So let's recollect before we carry out, because we said too many things. So the first thing that we said very categorically, that if you observe the inner integral, if they have variable limits, then the boundary definitions can be either inclined straight line or curved edges, depends on the boundary condition. And the second thing that we said, you always decide the region of integration. That is, now of course we are integrating a function over this region. If this function were to be 1, a constant, then we would have exactly got the region over which area of the region. But now how do you decide this region? By considering the limits of the inner integral. In fact, one of the lower limits is y equal to x square, that is parabola, and upper limit is y is equal to 2 minus x, because remember, you're first integrating with respect to y, so these have to be the limits of y, and these are the limits of x. So we could sketch this particular region very, very clearly, and we also could find out the extreme point by simultaneously solving the parabola and the straight line. This is the point where the two boundary definitions intersect with each other, and if you solve them simultaneously, you'll get x equal to 1, y equal to 1. Of course, this is quadratic, giving you two values, and the other value is that this straight line, if extended, if the parabola is extended, it's going to intersect here. So that will give you one more value of your x. But we need the positive value. Now, having done this, how do you actually write these limits? That's very, very important and interesting. I'll tell you a very simple technique, because what is look at what is the first order of integration? It is with respect to y. Then observe me carefully. What I do, I in fact start from the lowermost boundary and travel vertically all the way to the uppermost boundary. So these are the two boundaries which actually define this, of course, apart from the y-axis. So therefore, if I incept from the parabola and travel vertically all the way, I would be hitting the straight line. That is why my inner limit of y is y equal to x square, which is the parabola, and the upper limit is y is equal to 2 minus x, which is the straight line. And what about x? I again start from the y-axis, because that is one of the extreme boundaries, horizontally, and then I travel horizontally all the way and I hit the extreme point, which is 1 comma 1. So the y-x limits are 0, 1, right? So this is very clearly understood. Now what is our next goal? Split this, or change the order of integration. Splitting whether becomes warranted or not, we will find out. Whether this double integral becomes one more double integral, or it becomes double integral. Let's try and see. So here, let's try and see why exactly we should get a double integral if I change the order of integration. So the first thing is, I'm going to recast this. That is, we are integrating a function xy. I'm not worried about it. For me, the region over which I'm integrating is my concern. So first I'm going to integrate this with respect to x. All right. Then with respect to y. The given problem has integration with respect to y first, x next. So I have done the reverse of it, right? Dx. Now I will have to fix the limits. Now, earlier, if you saw my explanation, because my integration was with respect to y, I traveled vertically from the innermost boundary layer to the outermost boundary definition, okay? Boundary line or boundary curve, whatever you would like to call it, it doesn't matter. But here, what I have done, I have actually altered the order of integration. That means I will have to travel horizontally from the inception, because this is my boundary, right? This is my boundary of the region. I have to travel horizontally. Let us say I have got 2-3 options to travel. One, I can travel like one, I can travel like this, one, I can travel like this. Which should I adopt? The question is very, very simple. I need to have all the boundaries, you know, incorporated or included in my limits. If I choose to travel like this, I'll be including only the straight line. If I choose to travel like this, I'll be including only the parabola. If I choose to travel like this, what happens? I'll be incorporating a point. When do you think that both inner and outer integrals will have only the numerical limits? Because if I travel along this line, I would be hitting this particular point, which has a numerical value of 1 comma 1. I would be starting with x equal to 0 and ending up with 1. So because x is my inner integral, when do you think the integral would have a constant limit? When my boundary lines are absolutely straight. I'm talking about this box. So when the boundary lines are absolutely straight, parallel to y or x axis, you would have constant limits. Otherwise, you cannot. So therefore, it is inevitable that I will have to choose these two paths because I want to incorporate this boundary definition. I also want to incorporate this boundary definition. So it becomes obvious that I will have to split my integral into two, one for this triangle, one for this triangle with a curved edge. This is also a triangle, but one of the edges is a curved edge. So this is a triangle, a normal triangle, all the edges are straight lines, but this is one triangle whose one of the edges is curved, right? So therefore we got to choose two integrals. So let's try and write both those integrals. So how do you do that? So this is very, very simple. In fact, we have written over here, but let me write it in earnest for you. So this is the integral that we incepted with. Now let me write the two integrals that we are interested. Integral 1, I am going to write for the triangle with one of the edges as curved edge. That is, I am talking about this area. So the outer limits would be for the y, because the order of integration is such that the outer integration is with respect to y. So what are the limits? They are going to be the extreme values. You have to travel vertically starting from this point, that is y has a value 0, and if I travel vertically and hit this, because I am talking about this area, be careful, right? So what is the maximum value of y? So that is going to be 1. So 0 to 1, it does not change. But what about horizontally? Horizontally, if I travel right from the y-axis, what is the definition of y-axis? X equal to 0. And what is the definition of x-axis? It is y is equal to 0. You should clearly note that this is y-axis, this is x-axis. Okay, that should be made very clear. From y-axis, you are traveling all the way and hitting this parabola. And what is the equation of the parabola? Y is equal to x square. But you need the limits of x, because I want the value of x. So I obviously take the square root and I'll get x equal to root 5. That is, I need an expression for x in terms of y. I don't want an expression for x square in terms of y, because I am worried about the limits of x. So you are starting from this, which is x equal to 0, y-axis x equal to 0, and going all the way to x equal to root y. This defines a parabola, this defines my y-axis, and therefore xy that is being integrated. Now what is the order of integration? First with respect to x, then with respect to y. So this is exactly the integral that we have given over here. Clear? So that is exactly the integral that we have given you over there. So now I need to construct this integral. So how would I consider that particular integral? What are the limits? How do I go about it? Now, when it comes to the outermost integral, which is with respect to y, you have to travel vertically from this particular point to this particular point. Of course, it's going to have the numerical values, and the numerical value is 1 to 2, because you are incepting at y equal to 1 and ending at y is equal to 2. So therefore what happens? It is 1 to 2. And of course xy, first with respect to x, then with respect to y. That is perfectly all right. But now in order to fix the limits, you will have to travel from y-axis and you are going to hit the straight line. That is your second boundary definition, inclined straight line. Y is equal to 2 minus x. So you are starting from x equal to 0, because that is the definition of y-axis, and you are going to hit the inclined straight line. What is the definition of inclined straight line here? Y is equal to 2 minus x, but I need the expression to be expressed in terms of x, because you are seeking the limits of x, because you are integrating with respect to x. So the variable limits of x. So that is going to be represented by 2, x is equal to 2 minus y. X is equal to 2 minus y, because just bring the x to this side, y to that side, that will give you 2 minus y. So these are the two integrals that we have constructed. One for the triangle, normal triangle, one for the triangle with curved edge. For both we have established two integrals. If we add up these two integrals, this integral plus this integral, Or if I say this integral and this integral, if I add up those two integrals, this and this, I will get the original integral, because over this triangle, the function is evaluated by this integral, and over this triangle with curved edge, this function is evaluated. And also, interestingly, if you see the representation, we have constructed a vertical strip here, we have constructed a horizontal strip here. You might be wondering what exactly this is all about. You see, this perfectly mimics the process that we are trying to do mathematically over here. What exactly we do? If you looked at this, forget about xy, the function. Let us mimic as if xy is replaced by 1. Okay, so we are interested in the area of this particular region, which is characterized by y-axis, the parabola, and the straight line. Right? There are 3 boundaries. Now, if I integrate with respect to x first, what you will get? You will get a strip. You will get a strip which is going to be this. Because you are integrating with respect to x. Integrating with respect to x, you get a strip of variable x length. Variable x length. Because if you see the inner limits for both the integrals, are variables. You can see it is 2 minus y, it is root y. So both are variable. That means when you carry out the integration, first you get a variable x strip. Then what is the order of integration? Once you integrate with respect to x, you get a variable x that is represented by this strip. And then when you integrate with respect to y, what happens? Several of such strips are added from this limit to this limit. Several of such strips are added from this limit to this limit, giving you the total area. And the same thing happens for this also. Several of such strips are added to give the total area. But why vertical? Remember our original integral, it is here. The integration first with respect to y. If you mimic that xy is 1, then what happens? First, when you integrate, you will get a variable y strip. And subsequently, when you integrate it across, you will get infinite number of such strips covering this entire area. So, let us take a pit stop, because this was the first exercise. We have explained almost everything graphically. We will evaluate next. But before that, let us quickly summarize what we did, so that you take home things very, very categorically. So the first thing is, first we incepted with this particular integral. So what it said, you are integrating a function xy over area which is defined by the boundary conditions, okay, of x and y. So the first thing that you understood is, if the boundary definitions of the inner integral are variables, then you are not talking about a box area. That is, your boundaries are not parallel to x and y axis. They are either inclined straight line or parabola. And from the inner integrals of this particular integrand, what we constructed is this figure. Because you can see here that the moment I say y is equal to 2 minus x, I used the intercept form. I constructed a straight line with equal intercepts of 2, and that is what the straight line is, which is drawn in red. And the second one is y equal to x square. This is the lower limit. If you see y is equal to x square, why I say that? Because integration order is with respect to y. So y is equal to x square, y is equal to 2 minus x. So this gave us the parabola, and when we found the intercept point, it is 1, 1, and this is exactly the region over which this is evaluated. I also told, if you consider infinite number of sample points, and each point has got x and y coordinates, when you multiply and add up for all those infinite points, you get the value of this integral numerically. Okay, that's what this integral is doing. Next, having constructed, we had 3 options. Whenever I am integrating, okay, first with respect to x, then with respect to y, because here it is first with respect to y, then with respect to x. But what we have been asked, change the order of integration. So what we did, we said first we are going to integrate with respect to x, then we are going to integrate with respect to y. And in order to do that, I need to fix the limits. How do you fix the limits? One of the techniques I told you, because previously also how the limits are fixed here, because it is with respect to y, you are traveling from your lowermost boundary definition vertically to uppermost boundary definition. Never forget, lowermost boundary definition to uppermost boundary definition. How it is defined? From parabola to straight line. You are traveling from parabola to straight line. And when it comes to x, you are traveling from y-axis to the extreme boundary, from y-axis to the extreme boundary. Here also you are traveling from the lowermost boundary to uppermost boundary. Here also you are traveling from y-axis to extreme boundary, so 0 to 1. That is how it is fixed. That's very important. So here also, since I said my integration is going to be first with respect to x, I will have to travel from y-axis to my extreme boundary. But if I did that in the upper half of this area, then I would be incorporating only this boundary definition. And if I did that in the lower half, I'll be incorporating only this boundary definition. But if I travel along this middle path, I'll be confronting only the extreme point, which is just a point which has no boundary definition, which is characterized by a fixed value, right? So therefore, what was obvious that I had to split the integral into two. And if you see here, that's what exactly we have done. And how do you in fact fix the limits? For example, if you consider this upper triangle, the outer limits are quite obvious, because these are the extreme limits of y 1 to 2. That's what we have done, 1 to 2. And if you looked at the limits of x, which is the first order of integration, you can see that I incept my journey from y-axis and travel horizontally to meet this straight line. So y-axis is this is the straight line. And what about the lower triangle with curved edge? The same principle, 0 to 1, because 0 to 1 the y limits, and x you are traveling from y-axis to the parabola, y-axis to the parabola. But here you will have to note carefully, you will have to express everything in terms of x, because I need the limits of x. There must be a relationship which directly gives you the value of x, not the value of x square, and that should be noted carefully. That is where x square is equal to y, we took the square root and we said x equal to root 5. So this is what is very, very important. First, the order of integration is x, and then the x limits are given here. So now it is very, very categorically understood. The given integral is split into two integrals. We have understood graphically, we have understood the limits. Now let's move on and evaluate them numerically. Now, having understood every facet of the changing the order of integration, now let's try and evaluate the resulting integrals. Now, we in fact started with this, that is y is equal to x square to y is equal to 2 minus x, and then 0 to 1, and then the function to be evaluated is xy, and then the order of integration of course will be dy dx. Just for a beginner, though this is very, very obvious, if the order of integration is y, and if the boundary definitions are inclined straight line or curved edges which are variable, you can see that the limits are defined only in x and the outer limits are defined in numericals. This is to be noted, and this is equivalent to two integrals. Now please write along with me so that you have no difficulties. Even not looking at the figure, you should be able to understand what exactly you are doing when you change the order of integration. Of course, it's going to be dx dy and then dx dy. Now let's start doing it for the straight edged triangle, that is the upper triangle. So what will be the limits? 1 to 2. Now can you tell me what will be the limits? You are traveling from x-axis to the inclined straight line. So order of integration first with respect to x. So the limits must be in terms of y. So this is 2 minus y. Now please write limits along with me for the lower triangle with curved edge. So if you are traveling in the y direction from lowermost point to the uppermost point, it is 0 to 1. Again, you are traveling from y-axis, which is x equal to 0. to all the way to the parabola, which has to be expressed in terms of x because your integration is with respect to x. So y is equal to x square, take square root on both sides, you are going to get root y. So this is how I will have to practice. Now having done this, let us evaluate each one. First I am going to evaluate integral 1, then I am going to evaluate integral 2, right? So it is dx dy, given was dy dx once again. So now let's evaluate it. So how do you go about it? So the first integral has got the values 1 to 2, and then integral 0, and then it was 2 minus y, because you are hitting the straight line. I am talking about this area. And then is xy, and then dx dy. So when you are integrating with respect to x, keep y as constant, and as a consequence what you will get, you are going to get x square by 2 into y. So that is x square by 2, the limits, and then multiplied that by y, and then 1 to 2, and what are the limits here? 0, 2 minus y, and then your dy. So now how did I get? I integrated x with respect to x. I got x square by 2, and then y is a constant, keep it as it is, and the limits have to be substituted for the one which you have integrated, that is x square by 2. So 0 to 2 minus y. Forget about 0 because there is no additive member here, because when you put x equal to 0, the entire function vanishes. So therefore you are only worried about the upper limit. So therefore this simplifies to 1 to 2, and then y, this is 2 minus y whole square dy. Am I right? Because when you put the upper limit, it becomes 2 minus y whole square, and lower limit is 0, and there is half here which I would take outside. Clear? So now this can be integrated by expanding this a minus b whole square and then multiplying that by y. So how would you do that? That's quite simple. So you have half, you have 1 to 2, and then y into. So what you have here is y minus 2 minus y whole square, and as a consequence what you will get? You will get 4 plus y square minus 4y. Am I right? Because I am just doing a minus b whole square, a square plus b square minus 2ab, and then integrate that with respect to y. Now it's going to be very simple. Y is going to multiply every member inside the bracket, right? Every member inside the bracket, half is there. So I would directly write the final result here, because it is quite simple, basic integration for you. Because y when multiplies 4, you get 4y. When you integrate, you get y square by 2, of course, into 4. You can further simplify that, it becomes 2y square. What about the next term? Y into y square, which is y cube. When you integrate, you get y power 4 by 4. If you multiply minus 4y, what you will get? Minus 4y square. So 4y cube by 3. Right? So this is what exactly you will get. Now, the upper limit and the lower limit. This is very, very simple. So now I'm going to write half as it is. When it comes to upper limit, 2 square is nothing but 4. 4 by 4 is 16. 16 by 2 is 8. Minus. What about the lower limit? If you put y, if you replace y by 1, it becomes what? It becomes 2. So you get for the first term. What about for the next term? For the next term, you put y is equal to 2. You get 16 by 4. You get 4, and when you substitute 1, you get 1 by 4 for the next term. And then what about the last term? It is minus. When you put 2, you get 32 by 3. Okay, 32 by 3. And then minus. If you substitute 1, it is going to be just 4 by 3. Right? So this is what exactly you will get. So observe carefully, when you put 2, it becomes 4 into 4, 16 by 2, 8. And when you put 1, it just is 2, so 8 minus 2. Then what about the next term? It is 4 by 4. And then when you put 1, it is 1 by 4. And what about the last term? Minus, you keep outside. So when you put y is equal to 2, 32 by 3 minus 4 by 3. Now if you simplify all this, you get 6 here, you get 15 by 4 here, you get minus 28 by 3, and all that gets simplified to 5 by 24, right? So that is the numerical value of the first integral. Now let's try and evaluate the second integral and then sum it up. So what exactly we get for the second one? That is one with the curved edge, the triangle with the curved edge. It's quite simple. The limits of y happen to be 0 to 1, and then the limits of x happen to be x equal to 0 to root y, and this is also x equal to. So therefore you are integrating xy first with respect to x, then subsequently with respect to y. So now if I integrate x with respect to x, I get x square by 2, and y is of course going to be treated as constant. So the integration limits are 0 to 1 for that, and then here the integration the limits are going to be 0 to root y. 0 to root y. Am I correct? Because y is kept constant. X, when you integrate, you get x square by 2. 0 to root pi are the limits, and therefore if I simplify this, what I will get? I'll get, when I put root y, it becomes simply y by 2, y into y square by 2, and of course when you put 0, it is 0, so therefore it is y square by 2 dy, and then 0 to 1, and this if you simplify, what you will get? You will get 1 by 6. The reason being, when you integrate, you get y cube by 6, y cube by 6. The limits are 0 to 1. When you put 1, you get 1 by 6, 0, it goes to 0, so it is 1 by 6. So previously what we got? We got 5 by 24. Now I have got 1 by 6. Can I simplify this as 4 by 24? Because I can multiply and divide by 4. So what would be my final answer? My final answer would be integral 1 plus integral 2. So that would give me, one is of course 5 by 24, another is of course 4 by 24. If I add, it's going to be 9 by 24, which is 3 by 8. So this is the final answer. So therefore, a very, very important observation that you have made here is that whenever your boundary definitions have to be looked for, it is the innermost integral that gives you. And if they are variable, that clearly means that they are either inclined straight lines or parabolas. And if one of the limits is 0, that means either you are starting from x-axis or y-axis. Here of course your integration is incepting with respect to x, so therefore these must be the limits of x. So x equal to 0 would mean y-axis. Okay, and the second important thing is if you are integrating first with respect to x, then you get this particular strip, and then when you integrate with respect to y, this entire area is filled with many such infinite strips. The same process happens for the lower triangle also. And why did we have to split the integral? That is very interesting. That is because if you travel from the y-axis from in the upper half, you meet only the straight line. In the lower half, you would meet only the parabola. In the middle path, you will meet only a point. So therefore, this into two integrals so that you could incorporate both boundary definitions, inclined straight line as well as the parabola. So that was a very, very exhaustive discussion. For the next discussions, we'll just explain you what is what, and then more on. Hope you have actually appreciated what is what. And also recall that we did an introductory example for simple triangles to explain how double integrals in many situations get split into two integrals. So these two examples must completely give you the holistic picture, but now on it would be completely procedural affair for you. So let's move on. Well, engineering and math are absolutely inseparable. We Innoventions, day in and day out, try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.